Alright, in 6.7, it's a bit of review, so we're going to do a little bit of bell work here. I'm just going to go ahead and put all the answers on there, so when you're ready, hit play after you pause right now to try each one of these and see if you can get them right. And there we have it. We have 120 bacteria, doubling for 3 hours, which gives us 960 bacteria. Here we have decay because we have the 0.77, which is between 0 and 1, meaning it's decay. Here I have log base 2 of 64 over 4. What I did is I condensed the original problem to 64 over 4, which is 16. And I know that 2 to the 4th power gives me 16, so my answer is 4. Here I have log of 122 divided by log of 3. I use change of base there. I plug in my calculator, I get 4.37. I also could have used the math alpha math and just plugged in the 3 and the 122. And lastly, I have to take the natural log of each side, which cancels the e in the natural log, leaving me with negative 4.2 is equal to natural log of 0.015. Ooh, wonderful. Alrighty, here we have 6.7. Now 6.7 is basically like a combination of all the stuff from chapter 6, all the log properties. So we're really going to get back into those. Make sure you're following along in those awesome guided notes that I provided you with, because I'm so cool. Oh man, we've got some properties here. We've got the definition of a log, when we can go back and forth from log to exponential. That's awesome. The product property. Remember when we split these up, it becomes addition. If I want to go from addition to multiplication, I can do that as well. So back and forth, back and forth. Same goes with quotient, but quotient's related to subtraction. Now the power property is also super cool. If I have an exponent on the m here, I can put it out in front, and boom, I've got p times log base b of m. Excellent stuff. Now I have the exponential logarithmic inverse. Basically what we're talking about is anytime you have the same base here, so log base b of b, log base 2 of 2. We get a base, and then we're taking the log of that same number. It just basically cancels out, and we're left with x. Here it's really b to the log base b of x. So I have, let me write this part out a little bit better because it looks like the math type didn't work too well. B raised to the log base b of x. That's what we're really looking at there. Okay? So that one, boom. B to the log base b cancels. I'm just left with x. The one-to-one property. If I have the same base, my exponents equal each other. We've done that before. Here I have the same log base b, log base 2 and 2, log base 3 and log base 3. They cancel, and I'm left with x equals y. Usually I'll see something like 2x minus 7 equals 3x plus 5, and I solve for x, and that's just super fun. Now we also have our change of base formula, and I'm going to rewrite this a little bit better, so I don't really like how this is written. I'm going to go log of a divided by log of c. Okay, so what I'm going to do is I'm just going to hit log, put the number in on my calculator, divided by, of course I'm going to close the parentheses first, divided by log of whatever the other number is, and bada boom, bada bing, I'm going to get my answer. If I have the math alpha math key function on my calculator, I have one of the 84s that does that, then I'm all good. I don't even actually have to use change of base really at all, but it is a nice thing to know in case I forget that function, or if I'm using a different calculator, because maybe you want to impress your friends on their calculator and be like, I know how to do that, I'm super cool. So why don't we try a couple examples here? Well, this first one we want to solve it. Now whenever I have log and log, it's the same base. Now I have a 1 over here. If I had it equal to 0, I could have brought the other log over or something like that and done the one-to-one property, canceling the logs. But here, since I have this number over here, I'm going to have to just combine these two first. I'm going to have log of x times x minus 3 equals 1. And then I'm going to go ahead and distribute that x in. So I'm going to have log of x squared minus 3x equals 1. So I'm going to close those parentheses. Alright. Well, that's fun. Now, I really have log base 10, right? That's what's implied there when there's no log. I'm going to put this into exponential form. So I'm going to have 10 to the first, so 10 to the first, which is 10, equals x squared minus 3x. Oh, man. I know what I need to do now. I'm going to have to do some factoring and solving. I'm going to subtract that 10 over to the other side. So I'm going to have 0 equals x squared minus 3x minus 10, and now I'm going to factor and solve. Well, x and x, let's see here, what multiplies to negative 10 and adds to negative 3? Well, that's going to be negative 5 and positive 2. So I have negative 5, positive 2. I solve for x, I get x equals 5. I get x equals negative 2. Now, of course, I have to check and make sure that this works. If I plug in 5 here, I have log of 5. That's cool. If I plug in 5 here, I have log of 2. That's cool. If I plug in negative 2, oh, log of a negative number. I also get log of a negative number here with the second one. So I know that that can't work, but the 5 does work. So 5 is my only answer there. All right. Now, why don't you try this one on your own here. Let's try the next one on your own, see if you guys can do it. So pause the video, try it, and hit play when you want to see it worked out. Alright, for this one I'm going to go ahead and condense once again. So log of x times x plus 48 equals 2. So I'm going to have log, remember it's log base 10 of x squared plus 48x equals 2. And I'm going to put that in exponential form. So I'm going to have 10 squared equals x squared plus 48 x. Ooh, well this is 100 over here, right? 10 squared is 100. I'm going to set everything equal to 0. Once again, it's kind of the same type of problem. I'm going to have 0 equals x squared plus 48x minus 100, right? Because I'm subtracting 100 from the other side because 10 squared is 100. Hopefully you can handle that step all at once. So I'm going to factor it. What multiplies to negative 100 and adds to 48? Well, that would be negative 50 and positive 2. So I'm going to have x equals positive 50. I'm going to have x equals negative 2. Now let's see what works. If I plug in 50, I get a positive number. I get positive 98. Here I get positive 50, so that's cool. If I plug in negative 2, I'm going to have a positive number here. Oh, that's good. But when I plug it in here, I have log of negative 2. I can't do that. You can't do that. Nope. And I'm good with just 50. So 50 is my only answer. If I left the negative 2 there, I would lose points on my test. We love our points. Alright, next time we're going to solve on these, and I love me some solving. So I want to solve for x right up there. It's in the exponent, and I have this e here, and I know if I want to try and get rid of the e, I'm going to have to use that natural log on both sides, but I have to get the e by itself first. So first thing I'm going to do here is I'm going to divide by 4 on both sides. I'm going to have e raised to the 3x minus 5 equals, and I have 72 divided by 4 gives me 18. Now, here's what I've got. I want to get rid of that e, so I'm going to take the natural log here, and I have to do that to the other side as well. Remember, that's the inverse operation. It's like when I'm trying to undo multiplication, undo division. Same idea. So that cancels. I'm left with 3x minus 5 equals the natural log of 18. And I know that the natural log of 18, well, that's just a number, right? That's just a number. I'm going to leave it, though, like this, because otherwise it's a nasty decimal that I have to deal with. So the next thing I want to do is I want to add 5. So I'm going to have 3x equals the natural log of 18 plus 5. Now, if I could have, plugged that in my calculator, the natural log of 18, and gotten some kind of decimal, but then it's not going to be nearly as accurate. So I like to leave it like that. Plus, I don't really like seeing a whole bunch of decimals and stuff. It just looks messy. So the last thing I'm going to have to do is I'm going to divide by 3. So I'm going to have x equals, and I'm going to write out how you're going to plug it in your calculator. Parentheses, the natural log of 18, and you'll have to close the parentheses on that, or as John Baylor would say, close the parens, bro, plus 5, and then close your parentheses and then divide by 3. Notice how I've got my 2 parentheses on the outside, I have 2 on the inside. I'm all good. The whole numerator, this whole numerator up here is locked in by these parentheses, my super cool parens. So then once I plug it into my calculator, I'm going to get a nice answer of about 2.63 when I round it to the nearest hundredth. I just chose round to the nearest hundredth. Make sure you're always rounding correctly. Alright, why don't you try that second one. Hit play if you need help with it, or when you're ready to see the answer. Alrighty, for this one, same idea, but this time I'm going to divide by 8 because I want to get rid of that 8 in front of the e, and I'm left with e raised to the 2x minus 5 equals 7. Now I'm going to do the natural log of both sides just like last time. Boom. I'm left with 2x minus 5 equals the natural log of 7. Yes. Yes. So much fun. I'm going to add 5 to both sides, so I'm going to have 2x equals the natural log of 7 plus 5 This is exciting stuff right here. And then lastly, divide by 2. So remember, what I'm going to plug in my calculator will be this. It'll be x equals, and then it will be parentheses, natural log of 7 plus 5, close your parentheses, and then divided by 2. I was running out of room there, but I got it all in. All right, once we plug that into our calculator, you're going to get x equals 3.47. Oh, yeah. Make sure you're plugging these in your calculator. You want to make sure that you're plugging them in right, because you might be all confident and cocky and be like, whatever, I got it, Mr. Allen, I'm totally fine. But you might not got it, okay? So plug it in your calculator. Make sure you're doing it correctly, all right? Make sure you're checking those parens. All right, for these next 5 practice problems, I'm just going to toss the answers up there. All right, I'm not going to do any kind of explanation. You've already done these, the past ones. We already did them in the videos, so you should be able to handle these. But check your answers. If you want full work, whatever, check it out online. I've got the notes all written out. But for these, just going to throw the answers up there. So pause it. When you're ready to check your answers, hit play. Boom, there you go. The only one I'm going to explain is number 4 here. Remember, there's a little 10 in this spot right here. So we have 10 raised to the 4th gives me x, and that's why we have 10,000 is my answer. Oh yeah, some word problems. We just learned these the other day, so we might need a little more practice. All right, so I have an investment of $1,500 earns an annual interest rate of 8.2%. Compare the final amounts after 5 years for compounded quarterly and compounded continuously. Okay, so we have to do both. Well, if I'm going to do compounded quarterly, I'm going to use this formula right up here. So let's plug all of our numbers in. So there we have it. We've got my principal, got my rate over my number of times it's compounded. Since it's compounded quarterly, that's 4. And we have 4 times 5 up in the exponent there. How about for my continuously? I'm going to be using this formula for the continuously. Let's do it. Okay, so there's my other formula. Now we're going to work these out in our calculators. Right? Make sure you're plugging them in correctly and you're very careful. So what I'm going to have for this one for the quarterly will be $2,250.88. Man, it's a solid interest rate there of 8.2%. If you ever see that, take it. All right, so $2,250.88. Now for continuously, we have $2,260.23. So if you can do the compounded continuously, you're going to make a bit more cash, and we like our cash. So there you go. So this one here says, how long would it take for an investment to double at an annual interest rate of 7.5% compounded continuously? Well, let's see here. If I have $100, it's going to be $200 when it's doubled. $300, it's going to be $600 when it's doubled. Let's just do this. If I have $1, that means it's going to be $2 once it's doubled. Notice how I have my principal here. That's what I'm starting with. This is what I get, my A of t. That's the amount after a certain amount of time. Okay? And I'm saying that I'm going to double. Okay? And it wouldn't really matter what number I use as long as I have this here and this is double that. So we're going to have that 1 times, and we'll have e raised to the 0.075 times t. Because I don't know what t is. I'm going to solve for t. Well, if I get rid of that 1, I divide by 1 on both sides. No big deal. I have 2 equals e raised to the 0.075 times t. And let's take this back again. If this were, $500 and this were 1,000, when I divide by 500 on both sides, I'm going to have 1,000 divided by 500, which gives me 2. So see how it's going to work out regardless of what I start with? I'm still going to have 2 over here. Well, then I'm going to take the natural log of both sides because I want to get rid of that e. We've been doing that. So I have the natural log of 2 equals 0.075 times t. And then I divide by 0.075 on both sides. And what I'm going to put in my calculator will be this. Natural log of 2, close those parens, divided by 0.075. And that should give me my answer, which is going to be about 9.24 years. Really round it to whatever we want. In this case, it didn't say anything, so I just put nearest hundredth, so 9.24 years. Usually it might ask for like nearest year, in which case we do 9 years, but it would pretty much be your call or nearest year for most of these. Alrighty, we have a similar problem here. How long does it take for an investment of $5,000 to double if the annual interest rate is 6% compounded continuously? Well, this time we're actually given a dollar amount. Okay, well, and feel free to pause this at any time and try it on your own. If I'm given $5,000, I'm starting with $5,000, right? And I'm compounded continuously, so 0.06 times t. I don't know what t is going to be. Well, what's my investment going to be if I double that? Well, it's going to be 10,000. Now you'll notice what I was talking about in the last problem. If I divide this by 5,000 because I want to get rid of that, what's 10,000 divided by 5,000? It's 2, dose, if you will. So I get e raised to the 0.06 times t. And now I'm just like the last problem. I bet you could probably finish this out. Hit pause if you want, and then try and finish it out. So I have the natural log on both sides. Cross it out. I'm left with natural log of 2 equals 0.06 times t. It's still very similar to the last one. Divide by 0.06. What I'm plugging in my calculator is natural log of 2. Remember those parentheses. Divide by 0.06. And I'm left with about 11.55 years. If I were to round this one to the nearest year, it would be 12 years. But I decided to round to the nearest hundredth. So 0.55, 11.55. Not too bad. Here's something a little different. If it takes a certain amount of money, 3.7 years, to double, at what interest rate was the money invested? And we're going to be talking about compounded continuously. This one fails to mention that it's compounded continuously, but it is. So let's see here. If it's going to double, we know this one. We know it's going to be 2 over here, and we can just do 1 here. Those are simple numbers to work with. And we have e raised to the, well, I don't know what my rate is, but I do know that it's going to be times 3.7 because that's how much time I have. The same process applies. I'm going to divide by 1, which gives me 2 equals e raised to the r times 3.7. Take the natural log of each side. Gone. Natural log of 2. Remember, if it's like tripled, you're going to see 3 here instead of 2. It's not always going to be 2. All right? So I have r times 3.7. If I divide by 3.7, in my calculator I'll have natural log of 2 divided by 3.7, which equals about 18.7%. All right? What you get is 0.187 as your decimal, but remember, if you want to put that in a percentage, you got to move that twice, and you get 18.7. So that's the interest rate we would need if we wanted to double our money in 3.7 years. Any amount of money compounded continuously would take an 18.7% interest rate for 3.7 years in order for it to double. Awesome. So cool. Man, that's some great knowledge right there.